Okay, amazing. Okay, well, hello everybody. Hope everyone is having a great afternoon or evening or morning, depending on where you're calling in from. So today we're going to be continuing with Llama 2. So obviously quite a big beastly paper that came out from Meta a couple of weeks ago. So a lot to unpack. In the session last week, we went through the pre-training phase, which is this auto-aggressive part. We went through the supervised fine-tuning, and then we started to touch on the reward modeling and how the reward modeling is trained and so on. But we never then got to the reinforcement learning stage, which is what we'll be getting to now and explaining how the RL with human feedback is done. We still won't get through all of it, so there might be a final part 3 next week. But we'll get through the main meat of the method, and then there'll just be some evaluations left. So without further ado, let's get started. And I also decided today that we can do this based on the paper itself, rather than going through slides, because actually there's quite a lot of content here, and actually kind of going through it together, I think, is not a bad way of doing this. So in terms of where we got to last time, we got up to, so we went through all of this. We explained, yeah, the fact that there's, well, just maybe to start as a recap, actually, just so I'm not throwing everybody in the deep end so much. Let's take another quick look at the overall high-level overview. So basically, we have this pre-training phase where we take the pre-training data, which is this very, very large corpus of text data. We then do self-supervised learning, which is this auto-aggressive phase. And this then leads us to getting Llama 2, so the kind of base model, which they then do various evaluations on different benchmarks and so on. So this isn't really chat enabled. It's basically just an auto-aggressive large language model. They then get the first instantiation of Llama 2 chat, something that is primed for chat-based interaction. They do this based on supervised fine-tuning. So they take, handwritten examples of what good chat would look like, and they fine-tune it on these examples. And then we go through this iterative phase, this RL-HF phase of basically getting human annotation and human feedback to say which response is better, which response is worse, mark which of two they think is better and how confident they are. This can then be used to train a reward model. And actually there's 2 reward models, one for safety and one for helpfulness. And then with these 2 reward models, what you can then do is do reinforcement learning. And actually they do rejection sampling as well, which is kind of a variant of reinforcement learning in a way, a bit more based on energy methods. And then you can iterate on this. Then you can improve the model based on the reward. You can improve the large language model based on the reward model, and then you can get new prompts from the large language model to improve the reward model, and you iterate as you always do with reinforcement learning, and then you get this model that they will show, and I will show with some graphs that they then improve the helpfulness and safety of the model, basically. So this is making it much more human aligned, basically. So that's what we'll go through today. We'll then stop before the deep dives into the safety. We're taking this one step at a time, partly my own fault for not having time to read through the remaining 50 pages this week, but I've read through the next chunk of the technical stuff, so we can make a dent in this and add to the mini series we've got here going on Llama 2 at the moment. Again, as always, feel free to ask questions as we go through. For those that may be listening on YouTube, and for those in the room as well, feel free to raise the hand or ask questions at any point, but I'll stop every now and then just to check in with everyone. Okay, so let's go. So where did we get to last time? So we did fine-tuning, we explained that. We explained the reward modeling and how the reward models are trained, but we never actually got into how the reward models are used. And this is when we then move on to the next phase, which is iterative fine-tuning. So I'll go through the paper on a high level. We'll use the paper as a backdrop, but I'll try to avoid just reading it to you. We don't have slides on this session, although hopefully for the next session there will be. So we now get to, as I said, iterative fine-tuning, which is basically when they take the reward model and they apply RL in some capacity to the model itself. And they say here that yeah, as they receive more batches of human preference data, they're able to train better reward models and collect more prompts, and therefore train successive versions of these RL-HF models, which are referred to as RLHF1, well, V1, RLHF V2, etc., up until RLHF V5. So this iterative process that unfolds with RL. So they explored RLHF fine-tuning using two main algorithms, which actually in the final model they combined. So they used proximal policy optimization, which is a very well-established, at this stage with the rate of progress kind of canonical paper by this time, PPO from 2017, which is really the standard in the RLHF literature. For those familiar with RL, it's a policy gradient method, which means you need to collect on policy data. You can't apply this method with off policy data that you collected previously and doing things on a replay buffer. So therefore, because you're updating the gradient of the policy directly, you need to be constantly getting data that's related to that policy and was captured using that policy. And actually, as we'll get to, that's why they have this KL divergence loss to make sure that the new policy doesn't stray too far away into uncharged territory from the old one. So that's PPO. They use that. They then also do rejection sampling fine-tuning, where they sample K outputs from the model, and they then effectively select the best candidate using their award. And then they select this singular best candidate, basically, and then they fine-tune on these best cases. And they can say that actually in this case, you can treat the reward as an energy function, but here they go one step further and they don't only use this. I can only assume the other what they're talking about here from Deng et al., where they use the reward as an energy function and then they sample the highest reward at test time. They say here they go one step further and use this to select outputs for gradient update. So they actually not only use the reward function as a guide for selecting the best response, but they actually update the model itself based on these updates and do fine-tuning based on the best performing ones. Yeah, so then for each prompt, the sample obtaining the highest reward is considered the new golden standard. Again, similar to some previous work, and then they fine-tune the model based on the new rank samples, which reinforces the reward. I don't think they take the reward value into account, which makes this to me seem a bit less principled than PPO, because effectively you're kind of reducing the information in your reward function to simply being an optimal example selector, and you're not then leveraging the value of that reward, if I understand correctly, but nonetheless it seems to work well. They say the two RL algorithms may differ, in the first one being they differ in breadth, because rejection sampling, the model explores K samples for a given prompt. So you get this, with your temperature parameter, you get this big diversity of prompts. Whereas in PPO, you typically generate one sample for any given prompt. Whereas in depth in PPO, basically during training at time step T, so T here referring not to steps in the environment in RL, but actually the T and the training time, each iteration of training, basically. The sample is a function of the updated policy model from time T-1 after the gradient update of the previous layer. So in rejection sampling fine-tuning, they sample all outputs of the given the initial policy, then collect a new data set before applying the fine-tuned, similar to their supervised fine-tuning. But anyway, but basically, even with the rejection sampling, they end up doing this iterative approach, and this blurs the lines between the two, making them less pronounced on a high level. So there's these two approaches basically for using the reward model to impact the large language model, and that can either be with on-policy gradients, with policy gradient methods, basically in PPO, where you directly update the model parameters based on the reward itself, or you use the reward as a selector function to get the best singular example and then fine-tune on those examples to recreate them in a supervised manner. So two different ways of achieving similar end results. Any questions on that so far? Anyone in the room? Or anyone on YouTube? Another thing I'll quickly say is maybe James, just on the off chance that we get some questions on YouTube, just feel free to relay those to me, but I'll assume we're all good for now.
Yeah, no, all good so far.
Cool, good stuff. So what they do is until RLHF4, which is this fourth step in this iterative process, they only used rejection sampling fine-tuning. They don't explain why, maybe because this is a very, very long process with lots of labelers involved in each loop. I assume this takes many weeks and months. Maybe they just realized a bit late that PPO is good as well. I don't know, but until RLH4, they only use rejection sampling fine-tuning. After that, they then combined the two sequentially and applied PPO on top of the resulted rejection sampling checkpoint before then sampling again. Again, no real explanation as to why they decided 4 is the time to kick in PPO, but that's what they did. Okay, so then a bit on rejection sampling. Again, I'll get to these graphs when they're actually referenced, so we can have the full context. So then with rejection sampling, they perform it. Yes, this is interesting. They perform rejection sampling only with their largest model, and then all of their smaller models are fine-tuned based on the rejection sampled data from the larger model, and they therefore effectively distill information from the large model into all of the smaller models. So they're not independent, actually. When you have, Llama 2, I don't know what the values are, but 10 billion or 30 billion or something, then it's still actually used some information from the 70 billion parameter model, basically. Yeah, so the fine-tuned rejection sampling a large model and distilling, yeah, exactly. So that's an interesting point there. And then at each iterative stage, they sample K answers for each prompt from the most recent model, and they also score each of these given the best reward model accessible at the time of the experiment, and then select the best answer for a given prompt. So in early version of the model up to RLHF V3, the approach was to confine answer selection solely to the bag of samples from the preceding iteration. So for example, if you're training iteration 3, you would only use the samples that came from your previous iteration in version 2. But what they found, interestingly here, is that despite continuous improvement, it did lead to a regression in some capabilities. So they say that I'm just going to say V3 and not keep saying the four-letter acronym. So for example, V3 struggled more than previous versions to compose rhyming lines in poems, which we all know people love to do with ChatGPT. I wonder how much the kind of populism of certain usage patterns play a role here, because they have this, as I'll get to later, they have this whole innovation that relates purely to kind of the prompts like act as this famous person or only respond to me in this kind of way, and instruction-based stuff. So there's kind of a lot of the populism of usage of ChatGPT now coming into the methods they're doing to try to recreate that, which is interesting to see. But yeah, anyway, so it wasn't a very good poet when they only trained on the previous prompts from the previous version. And then so to mitigate that, they then basically use from various previous they sample from lots of the earlier iterations as well, basically. So yeah, in response on subsequent iterations, we modified our strategy, incorporating top performing samples from all prior iterations, such as those used in RLHF-V1 and RLHF-V2. Yeah, so that they keep this kind of large data set, which is actually not as on policy in a way. So you're actually using data from your very old policies as well, but they find that made it more robust, basically. So they don't present specific figures there, but it's demonstrated through enhancements that they just say in performance and effectively address the previously noted issues. Yeah, and it's also been, similar patterns have been noted before. So now we get onto a nice image they show us. So they illustrate the benefit of rejection sampling in figure 7. So let's have a look at figure 7. Basically what they're showing here is that as the number of, so this is assuming no training, assuming you just have your model and you generate lots of different samples for the same prompt, how good are those prompts based on your pre-existing reward model? So what you basically find here is, as you make many more samples, the median of the rewards doesn't really change. And in fact, you would expect that to be the case, because if you just, it's almost like a probability distribution or a normal distribution, the average stays the same, but you just have many more samples. You're going to have some terrible responses when you change the parameter and sample more. You're going to have some very good responses. And what they're basically showing here is that you actually get a lot of diversity, and when you just sample your current model more and more times, you end up getting some pretty good answers that are better than the one that you get on average, basically. Pretty much that's what it's saying. So it's basically showing that this rejection sampling has a shot at working, because if you do just randomly generate a ton of examples, there's enough stochasticity in the model, and you can, set the temperature parameter to a sufficient value that you do end up getting, better answers out of it. And then you can, of course, use these singular better responses to then do further fine tuning to push the whole model towards those better kind of responses that it is able to generate, but doesn't necessarily know are better than what it typically generates. So this is just a verification that importance sampling has a shot at working, and it seems to have a shot at working pretty well when you look at this curve. And this is only 10 samples, so I don't know what it looks like when you get further up, but I can imagine it, plateaus maybe 20 or 30 or something. Oh no, up to 100. Yeah, no. Okay, 10 to the power of 1, sorry. So yeah, 100. So maybe 150, 200 or so it starts to plateau. Right, so that's this is that point. So basically rejection sampling works because of this property of the randomness in the responses that you get. So they illustrate that in figure 7, the delta between the maximum and medium curves can be interpreted as the potential gain of fine-tuning on the best output. As expected, this delta increases with more samples. They don't show the plateau. I'm interested why they don't, but I guess maybe they had to, I don't know. I guess maybe it just wasn't worth showing, or just was quite computationally expensive to create the whole graph. But so as expected, this delta increases with more samples. Since the maximum increases, i.e. more samples, more opportunities to generate a good trajectory, while the median remains stationary. It actually increased a tiny bit, but I assume that's just random noise. There is a direct connection between the exploration and the maximum reward, of course, and the temperature parameter also plays an important role in the exploration, as higher temperature enables us to sample more diverse outputs. Again, so the temperature is this control on, how much randomness basically is present in the generations. So then we get figure 8, and what they talk about here is actually the role of temperature, and how, to begin with, after the supervised fine-tuning, the temperature is pretty consistent. Well, I'll get to the graph maybe to show you, but basically the temperature is pretty consistent with supervised fine-tuning, but when you start doing the reinforcement learning, the optimal temperature value changes, because of course you want the temperature to be set, which is this parameter. You want to set the temperature so that you get the best possible maximum reward for a given set of samples. Like, this is what you really all are like after, basically. If the temperature is so high that it just always generates, complete rubbish, basically, because you're too far off from the mean and everything is just, not good, then things can collapse. In that sense, if the temperature is too low, you're just going to be generating very similar examples to the mean, and you're not going to allow the model, to move further away from its mean, basically. So yeah, this temperature is a sensitive parameter, and what they say here is that, so what's this? This is the maximum reward. So this is after doing all the samples, what the maximum reward is and how that varies with temperature. So the temperature varies with color. Each of these curves represents a different value of temperature, and as the number of samples increases, this actually changes. And in the case of the supervised fine-tuned model, these are relatively stable. So each of these temperatures, the best one basically being, you want the temperature set such that for a certain number of samples, you want the maximum reward that you get to be the highest. So of course, the highest curves on the top of this are the optimal temperature parameters that you should be setting. The point being here that this varies. Once you've done the reinforcement learning and you've actually moved away from supervised fine tuning, the story changes, and the best actually change a bit. So you need to basically, as you're doing this reinforcement learning and each V1, V2, V3 comes out, you need to continually tweak your temperature parameter and keep assessing how the changing model is affecting its reliance on the temperature and its and how that correlates with, getting a good score. And you need to just keep adjusting your temperature, basically. This is like the nutshell. And what you see here is that the optimal, at the beginning, let's say the optimal was 1. I mean, maybe they've just normalized these, I'm not sure, but the temperature for the supervised model to get the best scores was 1. But actually, once you've done a few iterations of RL, this red one is no longer the top, and actually you're better to have 1.3, for example, or maybe 1.4, 1.3. So I guess they increase the temperature gradually throughout this RL phase. Anyway, just another interesting point of something that they need to optimize as part of this process as well. Okay, so that's kind of high level. They then give a little bit about just rundown on PPO, but it's a pretty high level view of PPO. I can quickly go through the main equations, but there's nothing too complex there. Any questions so far?
Yeah, there's one from YouTube from AN, and he asks, why do you think Meta chose to predominantly use? Why do you think they chose not to predominantly use the large multilingual data they have access to, and instead train Llama on more than 85% of the data consisting English?
Well, I certainly can't speak for Meta on that one. I don't know basically, but Meta, of course, don't use their proprietary data. So just one thing to say there is that they do this all on open data, and they don't, they're not going to, look at all the WhatsApp chats and so on, and they can't anyway. It's encrypted, but I think basically my understanding, and I don't know if this is totally correct, but my understanding is that the vast majority of open data on the internet is still English. For whatever reason, because it's the language that's spoken internationally. So that's one reason, maybe because a lot of the internet history is based in the US. I'm not sure exactly, but I think one of the facts is just that when you take these huge web crawl data sets, they end up being vast majority English, and this is what ends up happening, is my understanding. Yeah, maybe that will change over time, of course, but I think that's the case right now. Cool. Okay, so I get to PPO then. So where are we? Yeah, so PPO. So high level of PPO for those that aren't familiar with it. So PPO is 2017 paper, but they further train the language model following a particular scheme of a 2020 paper from Steenen and et al., which uses the reward model as an estimate for the true reward, human preference, and the pre-trained language model as the policy to optimize, of course. So during this phase, they seek to optimize the following objective, where you have your policy, pi, you then have your prompts sampled from the prompt dataset D, you have your generations sampled from the policy, and then you're basically trying to optimize your reward, which gives you these generations conditioned on the prompts, and this is the reward you're trying to optimize, basically. So and their reward function looks as follows. So they have this R hat C, which is the what's the C stand for? Combination, I guess. Yeah, piecewise combination. So they have this piecewise. So it combines the safety reward function and the helpfulness reward function, and this R hat C gets unpacked further down below. And then they have the typical KL divergence component with some parameter here, which basically measures the KL divergence is like what's the assuming, I think I get this the right way around, but I think it's like this is assuming this model distribution. If you were to get a sample from this, what's the surprise to get that sample, assuming that you are actually from this? So it's basically a measure of the divergence between two different probability distributions, basically. So a high KL divergence suggests that they're very different, and if they're the same, then there's a K divergence of 0, I believe. So anyway, the point of the KL divergence being, just like in an intuitive level, given that PPO is on policy and you need to keep generating data and you need to keep optimizing your policy based on that data you've just generated to keep it on policy, there is this risk that you end up going into a bad policy space and generating bad data that you then can't learn from. And effectively, a good way of stabilizing this is to make sure that your policy can't deviate too strongly too quickly. So you make sure that you're bound to keep your policy, to keep it bound to the previous policy to some extent, and make sure that therefore it explores more slowly and more stably than it otherwise could do if you're just trying to optimize the latest data that maybe in partial you could overfit very quickly and end up in a very bad policy space generating rubbish data, basically. That's my high level explanation anyway of PPO. Right, so they do that. So then now let's unpack this reward function a bit more. So basically, what do they have? So it's a piecewise combination of the safety and the helpfulness reward models. So it's actually not combining it. It's very much one or the other. And what they do is they first of all explicitly label prompts which they think are unsafe. So the prompt itself, like even ignoring the possible response you can get, the prompt itself is inherently unsafe. So they basically have this function that is pretty much just hand labeling of the prompts. So if it's an unsafe prompt, or if the safety value is sufficiently low, then the reward becomes entirely the safety reward. Otherwise, it's entirely the helpfulness reward. And I guess I thought about this a bit. I didn't have enough time to think about it properly, but it seems a bit strange to me because in a way I would have thought you want all responses to be like on some measure as safe and helpful as possible. They made this point that the two things are often directly conflicting, of course. So I guess if it's not unsafe, like it maybe just make the reward signal simpler if you just say, well, just make it as helpful as possible. Otherwise, like then we just need to like make sure that we you know, focus on the safety. But it seems a bit strange to me they don't add these together, and instead they just allow it to kind of switch like a step function between one or the other. But they don't really elaborate on that, so not too much to read into there. But it'd be interesting to know why this performs better than a simple addition or something. Yeah, and then they have this. They mentioned here that they find it important to whiten the final linear scores by reversing the sigma logic function, increase the stability and balance property of the K or penalty term. Didn't understand this actually, so if anyone does, feel free to write in the comments. But I mean, so just two sentences, but I didn't quite understand what they meant there. But yeah. Okay, then they give the model they explain just the high parameters, so they just use, you know, some pretty standard values, weight decay, gradient clipping, etc. But I think we need to dwell on that too long. Okay, and they train for between 200 and 400 iterations in all their models. They use evaluations on held up prompts for early stopping. So this is another question we had in the previous session, actually, where somebody asked, how do they prevent the RL from overfitting? And this is one of the ways they do that. So they have a held out set of prompts, and they can see then when they start to overfit, when the held out prompts are not performing well, and that's when they stop it. So that, you know, the RL does have this kind of validation set notion as well. Each iteration of PPO on the model takes about this long, a few minutes. Yeah, they use it's just implementation. They use this approach. They yeah, this is all just kind of implementation stuff. It's not that interesting, really. And then this is something that there's a question.
Yeah, Yashin Dal asked, so does temperature become a variable hyperparameter depending on the input, or does it stabilize to a sweet spot?
I think they I don't think they condition it on the input. I think they basically condition it on the iteration of the RL process. So on each new stage, and there's not that many of them, maybe I've forgotten now how many there are, but maybe 5 or 6 stages of this RLHF. I think 5 because they kind of did ... to 5. So on each of these, I presume they then create a graph like this, and they see which one is the peak, and then they set the temperature for that entire phase. Of course, they could kind of try to vary the temperature during sample generation, but I guess that just gets a bit too complex. So I think it's just fixed for each stage of the RL algorithm, if I understand correctly. Yeah, there's all kinds of things you could do here. You could like learn the temperature or something. But yeah, I think that's how they do it. Quite simple for now. Cool. So, and then, yeah, this is so. Yeah, then they talk about this whole thing here, which is system message for multi-turn consistency, and this whole section 3.3 is basically the question of how do we get it to perform well if we say, you know, act as Isaac Newton, or how do we get it to perform well if we say like end every question with an, you know, end every answer with an exclamation mark or something, which of course is a very common way that ChatGPT is used. And what they said, well, let's go through it. So yeah, some instructions would apply for the whole conversation. So act as some public figure, etc. And it should always respect the constraint throughout the entire conversation. Basically, they find that their initial RLHF models tended to forget the initial instruction after a few turns of dialogue, as illustrated in figure 9 left. So they show here, when you say to always answer with emojis, they remember for one message and then they forget about it. Whereas after they've done this GAT, G attention approach, then it remembers basically. Yeah. So to address this limitation, they propose ghost attention. Yeah, quite interesting term for that. So ghost attention, a very simple method inspired by context distillation that hacks the fine-tuning data to help the attention focus in a multi-stage process. GAT enables dialogue control of multiple turns. There's one thing I didn't fully understand here. So my understanding, I won't read through all of it, but my understanding is that they basically do new training where they generate this synthetic data set of of conversations which compose the user and the assistant, and then we can go through it, and maybe anyone can, assist with their understanding of this. But so they say, assume we have this multi-turn dialogue with users and A is the assistant. They define some instruction inst that should be respected throughout the dialogue. For example, it could be act as, or always do this after your responses or whatever. We can then synthetically concatenate this instruction to all of the user messages on the conversation. So we still don't know what this data looks like. Next, we can sample this synthetic data using the latest RLF-H model. And we know we now have a context dialogue and a sample with which to fine-tune the model in a process of large reduction sampling. And then they say, instead of augmenting all of the context dialogue's terms with this instruction, they can drop it in all but the first terms. This would lead to a mismatch at training time between the system message and the intermediate assistant messages. I found this hard to understand, to be honest, and I read it probably 6 or 7 times. I think they maybe need to explain this in a few more lines, but my understanding is that basically what they do is that, because they say then, apart from all but the first terms, they then mention that they simply set the loss to 0 for all tokens from the previous turns, including the assistant messages. My understanding here is that they have these unrolled conversations where they append at the beginning this instruction, and they explicitly train it so that several instructions later that you should be adhering to it, basically. So we have these idealized interactions where they are being adhered to. My understanding is that these are data sets created that are behaving as they should be. They've been created in whatever way they've been created, and then you give the instruction on the beginning one, and you do training such that it basically makes the prediction that you want it to do. This is how I understood it, but I read this a few times, I didn't quite get the details. And for the training instructions, we created a few synthetic constraints to sample from. So you enjoy something, speak in something, act as something. Interestingly, to obtain the list of hobbies and public figures, they asked Llama 2 chat to generate it, because they don't want to start expecting it to know about people who it doesn't know about. So they made sure that it knows, the people that this whole thing is trained on. To make the instructions more complex and diverse, we conduct the final instructions by randomly combining the constraints. So then you can do act as and do this, and in Napoleon that's only talking in emojis or whatever. So they combine them together. They also shorten it, so always act as Napoleon can now just become figure : Napoleon. These steps produce a supervised fine-tuned data set on which they can fine-tune Llama 2 chat. Exactly. So my understanding is that they use the RLHF model to basically, this is the next phase. They've done this RLHF phase. Now they're doing this ghost attention, and they basically do supervised fine-tuning on this hand-constructed data, is what I think. But if I'm wrong, then please let me know in the comments. And then they just do supervised fine-tuning on these, basically, where it is adhering to the instruction given at the beginning. And they say they turn the loss to 0, so maybe they do append the instruction to every user message, but they only have the loss applied to the first one. Oh no, okay, I actually understand it now. Working out on the spot. So the way they generate the ground truth is by appending it to every single one, because then it does work. It's good enough to do it on one turn. So it's good enough. Yeah, okay, got it. So it's good enough to do it after one, so they don't need to hand write down this huge data set that's ideally behaving with emojis. They actually do need to append it to every single user message to get the data that it should look like. But then when they do training, they want to say, actually, we should not have needed to add it to every single user question. We did to generate the ground truth data, but we shouldn't have needed to do this. And ideally, only mentioning it at the beginning should have been sufficient. So they keep it there to make sure that the data generation and the training is the same. So they keep the user appended message to all of them, but they set the loss to 0 on all of them but the first one, basically, so that you're teaching it to learn to do this when only provided the information at the beginning. Okay. Sorry I didn't get that moment before the call, but it's good good to get it eventually. Any questions on that at all? Okay.
No, nothing from my side, no.
Okay, cool. So then they do this GAT evaluation. They then do this GAT evaluation. So basically, they apply it. They apply it after version 3, and they show quantitative analysis indicating GAT is consistent up to 20 terms until the maximum context length is reached. They show this in appendix, but I think there's a lot of details we don't need to go into there. They try to set constraints not present in the training of GAT at inference time. For instance, always answer with haiku, for which the model remain consistent, as illustrated in figure 28. Do we need to go have a look at it? Yeah, right now, let's have a quick look. Figure 28 is in the appendix, so we're in our 17. After the conclusion, because it's the appendix, so where are we? Let's see this haiku one. Okay, 26, 27. Okay, here we go. So yeah, okay. Well, so they never mentioned haiku in the training set, but yet it's able to do that because it knows internally what haiku is, so it can generalize this, behave this way consistently, and it's learned that concept, which then generalizes outside of the specific instances that it's sort of training. So same here. I like anything to do with architecture if it's relevant, suggest something related. So you can ask a question that first has nothing to do with architecture, and then you ask just what would you recommend, and it starts mentioning, oh, you might like this architecture. So it's remembered this across multiple terms. Okay, so that's ghost attention in a nutshell. So pretty simple, but seems like it's a very sensible way to get this kind of desired behavior that we're all familiar with now from ChatGPT. They then show this graph. I'll kind of maybe zoom out on a bit of a high level for the last few. So they then show this graph, which basically shows, if I understand correctly, that so it's the self-attention across this conversation where you say actors Oscar Wilde. I think this is grouped into all the tokens. Actors Oscar Wilde give short answers, and you have this kind of back and forth conversation. And I think their point, which is quite a simple one, is that the left-hand side of each figure corresponds to the system message, actors Dr. Wilde. We can see that the GAT-equipped model, right? So this is the GAT-equipped model, maintains large attention activations with respect to the system message for a larger portion of the dialogue as compared to the model without it left. So I think what they're saying here is that they have this act as Oscar Wilde, and basically these two leftmost columns are brighter than these two leftmost columns, which is so I think this one here on the surname Wilde is stronger. That's probably quite clear, but maybe not the best illustration. Maybe if that's all the image is showing, they could have maybe showed a bit more focus. But yeah, but that's the takeaway there. So basically is able to remember these long horizon and place attention on things far in the past when generating the current response, basically, which is exactly what you would expect. And they could do more. It's very vanilla. It is pretty basic, but they can do lots more on this, of course. Okay, so now we'll get through a few. This is a real deep dive. I realize I probably could have done the Llama 2 presentation on a much higher level, but given its impact and given that the impact of chat-based models in general, I guess going into the weeds is not necessarily a bad idea. So let's now look at RLHF results. So, well, actually, a lot of these are just human-based. So basically, they make the point that evaluating LLMs is a challenging open research problem. It's really not clear how you should be doing this. There's no gold standard. So it's very subjective, of course. And there's questions, how far can it really go? To measure the robustness, they collected prompts from both helpfulness and safety and asked 3 annotators to judge the quality of them based on a 7-point Likert scale. The higher, the better. And they basically observed correlation between their own reward model as well as the Likert scale, basically. So they show this in figure 29. Oh, I can click it. That's quicker. I should have realized that last time. So yeah, so basically that positive correlation. So it shows that these 3, I think 3 seems a bit low, but anyway, there's these 3 assessors assessing on this Likert scale objectively, and their reward model, has strong calibration or correlation with it. Back up we go. So that's one result they quickly show. They also then show us that the takeaway being their reward model is modeling what you want it to model. It's not just modeling some kind of niche set of instructions that Meta have given to their Meta instructors. It is actually quite objective measure of safety and helpfulness. So that's that. They then showed this. So I'll just go through the graphs rather than going through every line. So they compare it to ChatGPT, a particular version number. So yeah, compared to ChatGPT, left the judge is their reward model on the left, so which may favor well, of course it will, because their reward model is exactly what the what the meta model has been trained on. It's kind of literally the exact objective, pretty much, it's been doing the training. So the meta model does better than ChatGPT on most meta reward model baselines. Whereas on the right, the judge is GPT-4, which of course should be more neutral. Now, what they do with this is they switch, you know, they randomize which prompt is given first and so on, so you know, GPT-4 doesn't know which comes from which and couldn't have any like positional bias or anything like this. And again, they make the point that when you get, you know, once they've done their furthest iteration, well, this shows a few things. It shows that the supervised fine tuning is not enough. Like, this is the very first version of Llama 2 chat that they get, and it's maybe better in 10% of the cases. Once they've done a bit more supervised fine tuning, it still doesn't get great. And then as they do their reinforcement learning iterations, interestingly, V2 really became a lot more harmful. It seems. I don't know why V2 became more harmful, although and it didn't get any more helpful. That's interesting. And then what happened then? Then it got more harmless, more helpful, and then it became a little bit less helpful, but more harmless. And then it just got way better here and here. So I don't know what happened between V4 and V5, but it seems as though there was very good annotations in that data set. And with PPO really helped as well. So maybe they realized they need to start doing PPO because this is kind of jumping around a bit. I'm not sure. Anyway, so this is where they get, and with the final one, they're more helpful than ChatGPT in 65% of the cases, and like 62% of the cases they're more harmless, based on GPT-4. So yeah, interesting to see there. Now, of course, they haven't done these results on GPT-4, and in fact, they're quite transparent, I think, about the fact that GPT-4 is significantly ahead of the curve on all of this, but it's still good progress to think that maybe the open source space is you know, only a couple of steps behind, really, because ChatGPT was the state of the art not that long ago. So yeah. So okay, and we've just done this. Yeah. James?
Yeah, just another question from Yash. So it's about GAT, and he asks, why not repeat such requirements with each message during inference itself, just because of the extra computational consumption? And then he goes on to say, repeat as in model repeating it itself, as it does with truth generation.
I think because you'll then need to have a very good instruction capture architecture. Like, it's quite hazy, right? Like, when is an instruction to keep doing something an instruction? You don't want it to only work when you do like act as famous person name, or you know, speak in this way. So ideally what you want to do is like give a few examples of that, and then the model itself learns the concept of repeated instructions so that you can give it very obscure things, as in the case in Haiku. I hadn't seen that before, and maybe the way you phrase the wording is different, and it should ideally have the concept of preserved instruction instilled, because otherwise you have to have this like binary moment in the inference of the model itself, which is like, is this an instruction to preserve or not? And it can be a bit hazy sometimes, I think. So I guess you want this to be kind of actually a concept and model understands itself to make it more flexible and robust. Yeah. So Malcolm says, right, I guess it also has to do with the context length. Yeah, it could have to do with the context length as well. That's probably true. But I think it's better on all counts, to be honest, to try to get the model to understand this concept. Makes it just, you know, more learned, more end-to-end, less kind of engineered in the final system as well. So figure 11, I think I've said everything there was to say about this. Yeah. And then we have human evaluation. So human evaluation is often considered the gold standard for judging models. They ask them to evaluate helpfulness and safety, and against all these kind of things. That they did an assessment on over 4,000 single and multi-term prompts. They use this for ChatGPT. They use Palm. They use various other open source models as well. And the final prompt count is shown in this table. See more methodology in this appendix. Yeah, okay. So I think they can add to what the results here. So shown in figure 12, which is here. So Llama 2 chat models outperform open source models by a significant margin on both single-turn and multi-turn prompts. Llama 2 chat 7B model outperforms MPT 7 billion on 60%. Yeah, has an overall win rate of more than 75% against equivalently sized Vicuna model and Falcon models. So basically, tall dark blue is good, low light blue is good as far as Llama is concerned. So it does pretty well here. Again, very close on ChatGPT. So pretty neck and neck. And when you look at the error bars, yeah, hard to say with like huge conviction, but it seems to have an edge. And again, it was only 4,000 prompts for this particular assessment. And again, prompts that are not part of the training. So these are all kind of independent, additional assessments to just kind of keep giving a bit more context. Then they talk about this inter-rater reliability, and they basically say, long story short, so inter-rater reliability is kind of just like what's the word? Like almost standard deviation or variance in the scores. Basically, when there's big differences in raters, it's a big uncertainty. When there's big agreement, then it's more reliable. And basically, their point being, I think they give some numbers, but basically on the more ambiguous stuff, when it's very, very close, everybody agreed less, and when it's really obvious, people agreed a lot more. So, for example, they say that with ChatGPT especially, there was a lot of variance in the assessors and what they thought was best or wasn't best, basically. And all the obvious limitations with this. So it's only 4,000 prompts. It doesn't include any code, I believe. They say that it doesn't cover real-world cases. It doesn't include coding or reasoning. They only evaluate the final generation. They don't actually ask people to evaluate the entire thing. It's just the final generation at the end. Could be more interesting to ask people to rate the overall experience of the model. Yeah, subjective and noisy, etc. So I thought I've decided to continue with the policy bit of, because it's PPO. I've decided to go with the approach of going quite deep into these, for better or worse. But I think having a good record of the nuts and all the deep aspects of Llama 2 is quite useful. Next time, it's been quite a long series on Llama 2. I'll promise to get it wrapped up in the next session. But then we'll go through the safety, the final conclusion, and the results, and then we'll have a deep dive on Llama that everyone can refer back to. We can finish a bit early, obviously, but are there any questions in the room? Any questions on YouTube that I can answer at all? Yeah, hopefully not
No, nothing from me.
too complex. Cool. And what I can obviously then just do to round up is say that, so again, like we've really looked at all aspects here, and actually what is really left now is just like the final points on how good is this. And there's a huge number of evaluations. We don't need to go through all of them, but we've really now understood all aspects of the fine-tuning, all aspects of the RLHF. The method is totally covered. And then it's just very much a case of how do we make this safe? Can we do things post-processing? So once we've got this trained model, what can we actually do in terms of systems integration and creating a product, which a lot of this then comes down to a little bit is kind of how does this get implemented, as far as I understand from having skimmed the last few sections, and how do we then compare this and know how well it's doing. So a few more graphs and results to show, but most of the meat, everybody will glad to know, is now covered. Cool. So I'll leave a few more seconds. Any other questions, thoughts, comments from anybody at all? No. Okay. Well, I'll let everyone get off early, back to their day. But yeah, thanks a lot for listening in, everybody. I promise we'll get through it soon. Not too much more to go. Thanks everybody. Bye for now. Bye bye.